Welcome to this comprehensive Pytorch Learning to Rank tutorial. We're going to build a neural ranking model using Pytorch and the MSLR Web 10K dataset. This tutorial covers everything from data loading and exploration to building a neural ranking model, implementing ranking-specific loss functions, evaluating with proper ranking metrics like NDCG, MAP, and MRR, and finally training and visualizing our results. Let's begin by importing all the necessary libraries we'll need for this project. Here we're importing all the essential libraries. We have NumPy and Pandas for data manipulation, Pytorch for building our neural network, Matplotlib and Seaborn for visualization, TQDM for progress bars, and collections for some utility functions. We're also setting up our visualization style for better-looking plots, setting random seeds for reproducibility, and checking whether CUDA is available for GPU acceleration. Great, we can see that we're using CPU for this tutorial. That's perfectly fine for learning these concepts and working with this dataset. Now let's move to data loading and exploration. We're going to load the downloaded data and explore its structure to understand what we're working with. Here we're loading the MSLR Web 10K dataset directly from Hugging Face. This is a standard benchmark dataset for learning to rank tasks. We'll convert the dataset to Pandas data frames for easier manipulation, and then check how many queries we have in each split. Excellent, the dataset has loaded successfully. We have 6,000 queries in our training set, 2,000 in validation, and 2,000 in our test set. This gives us a good amount of data to work with for training our ranking model. Let's explore the data structure to understand what information we have for each query. We'll look at the columns, examine a single query example, and understand the feature dimensions and relevance labels. So we can see our data has 4 columns: query, labels, features, and N, which is the number of documents. For our first query, we have query ID 1 with 86 documents. Each document has 136 features, and the relevance labels range from 0 to 3, where higher values indicate more relevant documents. Now let's analyze the label distribution across our datasets. This is important to understand the class imbalance in our data, which is common in ranking tasks where most documents are not relevant to a query. As we can see, there's a significant class imbalance. About 52% of documents have relevance 0, meaning they're not relevant. About 32% have relevance 1, 13% have relevance 2, less than 2% have relevance 3, and less than 1% have the highest relevance of 4. This distribution is consistent across training, validation, and test sets, which is good for our model evaluation. Let's visualize this label distribution with bar charts to get a better visual understanding of the class imbalance across our 3 datasets. The bar charts clearly show the imbalanced nature of our data. You can see how the bars decrease dramatically as relevance increases, with the vast majority of documents having low relevance scores. This visualization helps us understand that our model will need to handle this imbalance effectively. Now let's analyze query statistics to understand how many documents we typically have per query. This will help us understand the structure of our ranking problem. Interesting statistics here. On average, we have about 120 documents per query across all datasets, with a standard deviation around 70. The minimum is just 1 document for some queries, while the maximum goes up to 809 documents for training, 908 for validation, and 514 for test. This shows significant variability in the number of documents we need to rank for different queries. Now let's move to data preprocessing and create a custom Pytorch dataset. We need to handle the query document structure properly for ranking tasks, which is different from standard classification problems. Here we're creating a custom ranking dataset class that inherits from Pytorch's dataset. This class handles the special structure of ranking data where we have queries with multiple documents. We're implementing feature normalization using standard scaling, computing the mean and standard deviation across all features. The class stores queries with their associated features, labels, and document counts. We normalize features to help with training stability. After creating the datasets, we apply the same normalization statistics from training to validation and test sets, which is crucial for proper evaluation. Perfect, our datasets are created. We have 6,000 queries with over 723,000 documents in training, 2,000 queries with 235,000 documents in validation, and 2,000 queries with 241,000 documents in test, all with 136-dimensional features. Now let's build our neural ranking model. We'll implement a neural network with an attention mechanism for better feature interaction. Here we're defining our RankNet model. This is a feed-forward neural network with several key components. First, we have multiple hidden layers with RayLU activations and dropout for regularization. We're not using batch normalization to avoid issues with single sample processing. Second, we have a feature attention mechanism that learns to weight different features based on their importance. The attention module uses a bottleneck architecture to learn these weights efficiently. Finally, we initialize weights using Xavier initialization for better training dynamics. The model takes document features as input and outputs relevance scores. Our model is initialized with about 252,000 parameters. You can see the architecture with our main scoring pathway going through layers of sizes 512, 256, 128, and 64, with dropout for regularization. The attention mechanism has its own small network that learns to weight the input features. Now let's implement ranking loss functions. We'll create several different loss functions, including pairwise and listwise losses, which are specifically designed for ranking tasks. This is a comprehensive ranking loss class that implements 3 different loss functions. First, ListNet loss treats ranking as a probability distribution problem, using cross-entropy between score and label distributions. Second, RankNet loss is a pairwise approach that learns from document pairs with different relevance labels. Third, lambda-rank loss extends RankNet by weighting pairs based on their impact on NDCG. Each loss has different strengths. ListNet is efficient for listwise learning, RankNet is good for pairwise comparisons, and lambda-rank directly optimizes for ranking metrics. We're using ListNet for this tutorial as it's generally effective and computationally efficient. Now let's implement evaluation metrics. These are crucial for ranking tasks. We'll implement NDCG, MAP, and MRR, which are the standard metrics for evaluating ranking systems. Here we're implementing the ranking metrics class with 3 essential metrics. NDCG at K measures the quality of ranking considering both relevance and position, with higher positions weighted more. It's normalized by the ideal ranking. MAP, or mean average precision, focuses on the positions of relevant documents and averages precision at each relevant position. MRR, or mean reciprocal rank, looks at the position of the first relevant document. These metrics give us different perspectives on ranking quality. We test them with a simple example to make sure they're working correctly. Perfect, our metrics are working correctly. With this test example, where we have perfect ranking with the highest relevance documents at the top positions, we get perfect scores of 1 for all metrics. Now we're ready for training. Let's set up our training loop and evaluation functions. Here we define 2 key functions. The evaluate model function evaluates our model on a dataset by getting predictions for each query and calculating all our metrics. The train epoch function handles 1 epoch of training, processing each query, calculating the loss, and updating model weights. We skip queries where all documents have the same relevance since they don't provide ranking information. We also use gradient clipping to prevent exploding gradients. Now we're setting up the training configuration. We're using 3 epochs for this demo, though in practice you'd use more. We're using Atom W optimizer with weight decay for regularization and a learning rate scheduler that reduces learning rate when validation performance plateaus. We implement early stopping to prevent overfitting. During training, we track the loss and all metrics, save the best model based on validation NDCG at 10, and stop early if performance doesn't improve for 3 epochs. Training is starting now. In Epoch 1, we achieve a training loss of 4.62 and validation NDCG at 10 of 0.41, with MAP of 0.59 and MRR of 0.78. This is our first model, so we save it as the best. In Epoch 2, the loss decreases slightly to 4.6, and our metrics improve with NDCG at 10 reaching 0.41, so we save this as our new best model. By Epoch 3, we see further improvements with the loss at 4.6 and NDCG at 10 reaching 0.42. Training has completed successfully. Now let's visualize the training progress and analyze the model's performance. We'll create plots showing how our loss and metrics evolved during training. Here we're creating 4 plots to visualize our training progress. The training loss plot shows how the loss decreased over epochs, indicating learning. The NDCG curves show improvement across different cutoff values, with NDCG at 10 being our primary metric. The MAP and MRR curves show steady improvement, reaching good values by the end of training. These visualizations help us understand that our model is learning effectively without overfitting. Looking at these plots, we can see nice learning curves. The training loss is decreasing steadily. The NDCG values are improving across all cutoffs, with higher cutoffs generally showing better scores. MAP reaches about 0.6 and MRR reaches about 0.8, both showing good performance for this challenging dataset. Now let's do our final evaluation on the test set. We'll load the best model we saved during training and evaluate it on the held-out test data. We're loading our best model that was saved during training, then evaluating it on the test set with multiple cutoff values for NDCG. We display the results in a clean table format and create a bar chart visualization of all metrics. This gives us our final assessment of model performance on unseen data. Excellent results on the test set. We achieve MAP of 0.6, MRR of 0.81, and NDCG values ranging from 0.38 for NDCG at 1 to about 0.45 for NDCG at 20. The bar chart shows all metrics clearly, with MRR being our strongest metric and NDCG improving as we consider more documents. These are solid results for the MSLR Web 10K dataset. Let's look at some example rankings to better understand how our model performs on actual queries. This function shows example rankings from our model. For each query, we display the predicted ranking alongside the ideal ranking based on true labels. This helps us understand where the model succeeds and where it could improve. We show the top 10 documents for each query with their relevance labels and predicted scores. Looking at these 3 example queries, we can see interesting patterns. In the first query with ID 27913, our model achieves an NDCG of 0.56. It correctly ranks some relevant documents high, but misses the document with relevance 2. In the second query 5308, with NDCG of 0.56, the model does well identifying relevant documents in the top positions. For query 20008, with NDCG of 0.45, the model gets many relevance 1 documents correct, but misses the single relevance 2 document. These examples show our model generally identifies relevant documents, but sometimes struggles with the exact ordering. Finally, let's analyze which features are most important for ranking. This will help us understand what signals our model relies on. We're analyzing feature importance using a gradient-based method. For a sample of queries, we compute the gradient of the model's output with respect to input features. The absolute values of these gradients tell us how much each feature influences the ranking scores. We aggregate this across multiple queries to get overall feature importance, then visualize the top 20 most important features with a bar chart. The feature importance analysis reveals interesting patterns. We can see that features F91, F75, F89, F74, and F90 are the top 5 most important features for our ranking model. The importance scores drop off gradually, suggesting the model uses a combination of many features rather than relying on just a few. The color coding in red, teal, and blue helps distinguish the importance levels. These top features likely capture key relevance signals in the documents. Now let's wrap up with our summary and conclusions. This tutorial has demonstrated a complete learning to rank pipeline using Pytorch. We've successfully processed the MSLR Web 10K dataset, understanding its query document structure. We built a neural ranking model with attention mechanisms for better feature interactions. We implemented multiple ranking losses, including ListNet, RankNet, and LambdaRank. We properly evaluated using ranking-specific metrics like NDCG, MAP, and MRR, and we train the model with proper validation and early stopping. The final model achieves good performance on the test set, demonstrating effective learning of ranking patterns from the features. The key takeaways are that learning to rank requires special consideration for the query document structure. Proper evaluation metrics are crucial, attention mechanisms help identify important features, and the choice of loss function significantly impacts performance. For next steps, you could experiment with transformer-based architectures, try ensemble methods, implement more sophisticated loss functions like lambda-mart, add query-level features if available, or fine-tune hyperparameters for better performance.